Right, we are live.
All right, I'll give it a minute or so before we let people in. All right, I'm going to admit and disable the waiting room. Andrew will let you know when we can start. Welcome, everyone. While everyone is flowing in thick and fast at the moment, through Zoom and through our YouTube channel. I just want to give it another minute. All right, I think we will get started. Thanks everyone for joining us. Good morning, afternoon, and evening from wherever you're joining us from. Welcome and thank you so much for joining. Today's webinar is AI, drones and satellites, tech skills geoscientists need or get left behind. This session is proudly hosted in collaboration with the American Institute of Professional Geoscientists, the Geological Society of South Africa, the West African Institute of Mining, Metallurgy and Petroleum, and the Geological Society of Zimbabwe. We are delighted to have such a diverse audience joining us from across the globe today. Over the next hour or so, you'll hear from leading experts who will share how emerging technologies like artificial intelligence, drones, and satellites are transforming geosciences. These tools are not just changing the way we collect and interpret data, they're shaping the future of our profession. Just a few housekeeping rules. You will notice that you are all muted with your cameras switched off. This is to save on bandwidth and to just monitor the usage of the webinar platform. So before we begin, just to let you know, each speaker will have 15 minutes for their talk, followed by 5 minutes of direct questions for that particular session. Following these presentations, we'll have a longer Q&A session at the end for participants. Please post your questions in the chat box, and we will be monitoring those, and we will pose those questions to the panel at the end. As I mentioned, keep your cameras and microphones off for the duration. The session is being recorded and will be available on the YouTube page. All right. Now it is being recorded. All right. So this is our esteemed panel of speakers this evening. We will post their detailed biographies in the chat for you, also for you to have a more in-depth look at. These are the same biographies we have posted on our social media posts and everything like that in case you've missed them. All right, so with that, let's get started. I would like to introduce our first speaker, David Hodgetts, who will be talking to us about digital outcrop modeling with drones, a beginner's guide. Over to you, David.
Okay, thank you very much. I'll just share my screen. Right, okay. So, hello everyone. Thank you for joining this webinar. I'm going to talk to you about digital outcrop modeling, what it is, why we do it, and hopefully encourage you to get out there and try doing some of this for yourself, because it is very easy to do it now. First of all, talk a little bit about what digital outcrop models are and how we've made them in the past and make them now. On the screen here, we've got two different examples of how we would build a digital outcrop model. A digital outcrop model is an accurate three-dimensional representation of a real geological exposure that's correctly scaled and georeferenced correctly, so you can make accurate measurements from it. On the left-hand side, we have a model that was created using a LiDAR. Now, this is how we started building outcrop models about 20 years ago, using a terrestrial laser scanner. You put the scanner on the ground on a tripod, it fires a laser at the outcrop, measures the 3D position, does that thousands, tens of thousands, millions of times over, and you get a three-dimensional representation of the outcrop. The great thing about LiDAR is that you have a specification that comes with the equipment that tells you exactly how accurate it is. But the downside is that it's expensive. When we bought this LiDAR system 20 years ago, it cost us around £90,000. And a similar kind of system now is similar cost. They're smaller, they're faster, but haven't really come down in price. But then we go to the model that's on the right-hand side. What you're looking at on the right-hand side here is the Silurian from Dumfries and Galloway, an outcrop called St Ninian's Cave. This was collected just using a camera and nothing else. So I walked along the outcrop, took lots of photographs, and then processed them afterwards to produce this three-dimensional model. This process is called structure for motion. It's kind of photogrammetry. And it allows us to build models that look the way a geologist expects the rocks to look like. It's photorealistic, and you can make measurements from it. You don't necessarily know the accuracy as well as you know with the LiDAR data, but it is incredibly cheap to do. And just the software to generate the models, there's open source versions of it available that you can use to generate data sets just like this. The scale bars that you can see in all of these images, if they're red and yellow, they're 5 meters. Why do we go about, why do we actually do this? Why do we collect and build outcrop models? Well, Burnham et al. Produced this paper in 2022, which describes the different reasons why you might want to build digital outcrop models. I'll just go through a few of them. So first of all, we have accessibility. If you've got a digital outcrop model built of your study area, you can make measurements from parts of that outcrop that you can't normally get to. If I'm out in the field, I can only measure from bits of the outcrop I can physically reach. If I want to take a sedimentary log, I am limited by where the safe access is through an outcrop. So digital outcrop models allow you to get to parts of the outcrop you can't normally get to. Following on from that, the accessibility, there's also inclusivity. It allows people who can't normally get to that outcrop to be able to see it and interact with it in 3D. And there's a whole range of reasons why we might not be able to get to the outcrop. And that some of those are things like in some companies, you can't do field work anymore because the insurance is too much, or perhaps the field area is just too dangerous to go to. So you can take those outcrop models back and use them and give them to other people. They enable us to do quantitative research. We can make high quality measurements from the outcrop models. Field geology has traditionally been quite qualitative, but this technique allows us to be a lot more quantitative and collect high quality data. It enables us to our interpretation to be reproducible, our work to be reproducible. So we can give these data to other people and they can go away and try and reproduce the work that we've done. Reproducibility is difficult in field work because it always involves going into the field. This helps improve on that. And then finally, it allows us to reevaluate interpretations and models that we've created in the past. This is also important for when you have outcrops that no longer exist because they've been built over or they've become vegetative. You can then go back and reinterpret them and reevaluate. Well, I started doing this kind of work back in the late 90s, and in the early 2000s, in 2002, I had a go at building my first photogrammetric derived model. The outcrops you see here are from the Tanqua Karoo turbidites in South Africa. And I was working on as a postdoc on a project. We're looking at these, and I had an idea that I could reconstruct some of the outcrop data using photographs. And there's a technique that was used at the time for building elevation data sets from stereo image pairs. And I applied that to photographs taken in the field. And you can see, sorry, you can see on the bottom image here, these are tie points that I had to put in manually. And there's some evidence that you can see a change in the slope on this data set. On this one up here, you can see that there is a gully, and I've got a bit of an interpretation on it. And then this one here, we've got some breaks of slope. So it's starting to pull out that there is some three-dimensional information held in those photographs that we can extract. However, it wasn't very good. Move forward to 2023, a couple of years ago, I found the same data set on some CDs shoved at the back of a cupboard, and I put exactly the same data set through modern photogrammetric software, and this was the result that came out of it. And you can immediately see the difference. Even with old photographs, we're able to produce very high resolution, accurate models, which we're able to go in and make measurements from. On the bottom left, you can see a surface dip attribute, and on the bottom right is an attribute that tells you about how flat the surface is. So it helps you identify things like fractures and bedding planes and faults if they're exposed as a flat plane. So that's how the technology has come on in a relatively short amount of time. We're able to produce these really detailed, very accurate models that we can go ahead and interpret. How do you do this? You can do it really simply just with a mobile phone, just taking photographs and walking along an outcrop. Or if you want to get a little bit more advanced, you can use a drone. Now, you don't even have to use an expensive drone. You can use something like a DJI Mini 4, which are not too expensive. They're still quite an outlay, really, but very small, very compact, very easy to put in your backpack. And when you're out in the field, you can collect photogrammetric data sets very quickly using these drones. And we use the Mini 4 as our main workhorse for collecting outcrop data sets because it's so convenient and easy to use, very easy to fly. How do you go about doing this? There's a couple of different approaches that you can use. So I've outlined two sort of main tech stacks that we have, technology stacks. Our open source low cost stack, which we can just use a mobile phone or basic digital camera. Open source software for doing the photogrammetric reconstruction. Meshroom, very easy to use. Basically, you just put your images in a folder and press go, and it'll do it. And then you have something like Cloud Compare, which you can take the models out of Meshroom and use to do interpretations. There's even additions to Cloud Compare, like the Compass plugin, that allows you to do basic geological analysis. If you want to go more advanced, you can use a mini drone like the Mini 4 Pro, or more complicated drones, more advanced drones. Do the processing in a commercial software like Pix4D, which gives very good results and is faster. And then you could do your interpretations in something like VRGS. And any one of those parts of the tech stack, you can swap in and out different sections of it to suit your needs at the time. Now, I've mentioned the phone camera. If you've got a modern iPhone, one of the iPhone Pros, it has a LiDAR built into it, and you can use that to build 3D models. But what I've done here is a comparison between three different ways of building the same outcrop model. We have the phone LiDAR, just using the camera on the phone, and then collected using a modern digital SLR. And you can see they're all giving very good results. The phone LiDAR looks really clear and crisp. The phone camera looks great. The mirrorless camera, probably should have spent a bit more time working on the exposure settings, but it's when you actually look at the detail of the mesh underneath, you see that the phone LiDAR doesn't give you as good a result, as much detail as you can get from your phone camera or from a digital SLR. So the point I want you to take away from this is that you don't need to spend a lot of money to get good results. This is just done with photogrammetry and you're getting better results than you do with the iPhone LiDAR. Well, what can we do with this data once we've collected it and started to process it? We have on the screen here, this is the Whitby mudstone. And I've done some interpretations on here, some structural measurements. On the top right, we have a false color image, which combines the dip direction, and how flat the surface is. And on the bottom right is an attribute that shows just how flat the surface is. And combining all those together, we can use that to help us interpret our fractures. And we can get on the bottom left here, see a stereo net. And as you're doing these interpretations, you can see your stereo net building up in real time on the screen as well, which is a great way to work with structural data and to understand, say, the distribution of your fracture data sets. We can also do automated fracture extraction using the surface attributes that we generate. And this is what we've got here, where we've pulled out lots of patches of vertices within the mesh that define the different fractures, so nice flat planes. And then we can plot all of those up onto a stereo net, sort of in a more detailed way, to see where our main fracture data sets are. Now, what I've got here is a little worked example of how we use this to solve a field problem. I used to run field trips at the University of Manchester in the UK, and we would go to this outcrop, which is on the Yorkshire coast. It's the Flamborough Chalk, and we would stand at the same viewpoints as we've got here and look at this fault, and the question would be, is this extensional or is it compressional? And because it's so thinly bedded, it's really hard to work it out when you're in the field. And there's been a lot of discussion as to what the nature of this fault is. So what I've done here is we're pulling out a image off the outcrop of on the one side and just moving it around there, and you can see that it matches up. And then I'll pull that panel to the other side of the outcrop, and let's see if we can work out where it fits. This is a recording. I'm not doing this live, by the way. This is just a recording of me doing this. So there we can start to see, does that match up? Maybe not. But if I move it there, move it in, now that does seem to match up. You can see it matches here and up here as well. And we'll just check again a little bit further along. Yep, we got a nice match. So that has shown that just using the outcrop data, the digital outcrop data set, with a little bit of programming, a little bit of software engineering, you can solve the problem. So we know that this outcrop now, this fault here, is a thrust. And that's something that has been debated in front of this outcrop for a long time. Once you actually see what the correlation is, it's really quite obvious now when you go back in the field. But unless you've seen it before, it's one of those things that isn't that clear. And then we can take that forward by doing some interpretations, split our outcrop model along where we've got the fault, and then do a simple jigsaw puzzle restoration to put it back to how it was. Another thing that we can do, we've got two data sets here, collected 5 years apart. This one was with a Phantom 4, and then the second one down here collected with a DJI Mini Pro 3. And I did this to really compare the behavior of the two drones. But what I was able to do once I'd collected it was produce a difference map between the two data sets. And what this is showing that over 5 years, how the geometry of this cliff face has changed. And the bright areas is where you've got high amounts of erosion, so up to 4 meters. And then the gray areas are where there's been very little or no erosion at all. And it's really pulling out that there are parts of the outcrop where we've had more erosion than others, and showing very nicely that the main erosion is occurring around where the fault is. And there's a fault just here. And that's as you'd expect. The fault is a area of weakness in the cliff face. And that's it. So that's an overview of digital outcrops, what you can do with them. And when we put it all together, you get a model that looks something like this, where we have fracture interpretations down here, modeling a fracture network, scale bars of 5 meters. There was a fault interpreted there. I've mapped on a interval on the outcrop. We have some surface interpretation with labels showing what the different layers are. And as we move on, got the different seams. So these are ironstone seams that have been in the past mined for iron ore. And then we've got our outcrop model integrated with a digital elevation model. And of course, you can integrate other data in there as well. So we can put things like our stratigraphic column, show where we are in the stratigraphy, and we're at the Cleveland Ironstone Formation in the Lower Jurassic. And that is a very brief introduction to digital outcrops and what you can do with them. So I think we're ready for some questions.
Thanks very much, David.
Thank you very
Go for it,
much,
Malcolm.
David. This is a wonderful presentation. Yeah, it's time for questions and answer. We have a few minutes to take some questions. Yeah, I can see some questions here. David, can you please name some of the softwares you were using for processing the data model?
Okay, I use my standard piece of software for processing the photogrammetric models is Pix4D. I would, if you want to go, I mean, obviously Pix4D is commercial software. If you want to go open source, then use Meshroom. I think is a very good place to start. Meshroom gives you a lot of processing functionality and produces very good results.
Wow, that is awesome. Thank you for this great insightful answer. There's still another question. Like in that example that you gave, like how many photos went into it and 1 day worth of field work to collect?
Okay, this model that's on the screen at the moment, this took me less than an hour to collect the data. And this was done with a Phantom 4 drone, so this is quite some time ago. There was about 500 images. The St. Ninian's Cave example I showed at the start, that was about 2 hours to collect the data and was just with a handheld camera. You can collect very large data sets quite quickly. In terms of the number of images, I've been processing images recently with 10,000 images in them. You can expect that to take a couple of days to process. But with 500 images, you can process it in a few hours.
Okay, because we have a few time left, let us just take one question before we move to the next speaker. Are there any significant difference in accuracy of field-based measurement with respect to image-based measurement?
Generally, no. I think you've got, in some ways, you can get more accurate data from the digital outcrop models because you have more flexibility over where you can collect measurements from, and you can choose better areas on a much larger outcrop to be able to collect the data. It does also very much come down to the quality of the data itself. So if you go back to some of the data sets we collected 20 years ago, there was a bit more dispersion in the outcrop data sets when you looked at your results, but the data sets that we're collecting now, as long as you're assuming that you're making a measurement on something that's, say, greater than like 10 centimeters, then you can get some very, very good measurements that are as good as, if not better than the ones you get in the field. Where the problem comes is if you're going down to really detailed measurements like grain size, or if you've got very small orientation surfaces that you're trying to make measurements from, that can be problematic.
Well, thank you very much for these insightful answers, and your expertise is greatly appreciated. So thanks for the questions as well. Let's move to the next speaker. The next speaker is Professor Paul Cleverly. He'll be talking to us on the geosciences meets large language models. He'll be expanding on the intersection between geosciences and artificial intelligence. So please welcome Professor Paul Cleverly. The stage is yours.
Thank you very much, Andrew. And I'm going to switch my camera off because I'm been having some Wi-Fi issues. So I will check that you can hear me from time to time. So let me just share my screen. Can everybody see that?
Yep.
Yeah.
Great, thank you. Well, great presentation from David. I'm delighted to be here today. My name's Paul Cleverly. I'm a geologist and computer scientist by background. I first started using language models in geoscience probably about 10 years ago, surfacing lithostratigraphic analogs just based on the patterns of words in large volumes of text. So I'll be sharing how we can use different ways we can use language models in the geosciences, steering a sort of pragmatic course between the hype, of which there is a lot around language models, and also the negativity and pessimism on the other side of it. We only have 15 minutes, so I'm not going to go into too much detail, but I'll cover the background to language models, how we can use them for different tasks, build LLM-based applications or agents, and then introduce a model for AI literacy. So, what does it mean to be literate in artificial intelligence for geoscience, and then finish off with a summary. And just to show how far we've come, this is an image completely AI generated, which you can see is described on the image there. So when ChatGPT first emerged, towards the end of 2022, it rapidly became the fastest adopted app in human history. Staggering 1/8 of the world's population now who are online, and we mustn't forget a lot of the population are not online. Voices are not in this room, and we're now closing in on about 1 billion users a week. So we have a lot of people using generative AI in all sorts of ways. Some surveys show around 70% of students, university students, tend to be using generative AI, a bit lower in the workplace. Anything from asking questions, identifying sources, helping refine writing, and building arguments and helping ideation. And from those surveys, it's about split. So 48%, this is a global survey, about 48% believe the benefits of AI outweigh the negatives. But I think most people are concerned, range around privacy, security, the risk of misinformation, to wider impacts it may have on our own cognitive abilities and what bad actors can do with it. And of course, although it's called artificial intelligence, these tools are not intelligent, but they can exhibit intelligent-like behavior in certain tasks. Now, the maths around large language models is complex, but a lot of the concepts go back to the 1950s. I think it was Firth, 1957. You shall know a word by the company it keeps. So by learning which words occur near other words for a given context, if we run that through massive amounts of volumes of text and images on the internet, we can create a statistical model that can predict what might be the next word given any particular context. Now, there are many free-to-use language models. There are closed, in other words, you have to use them online. And they're free to use in a basic form, and then pay to use for some of the more advanced features. And then we also have open or open weight models, which can be locally downloaded. So you can download it and run it entirely on your machine or your own infrastructure that no one else can see. They tend to be lower performance than closed models. If you see the table on the right, you'll see the current leaderboard, and the open weight models you see there just towards the base there, although that gap has been closing over the last few years. So one thing to bear in mind is that this open source open issue, because although we may say that language models might be open source, training data and methods have not been released. So they are not open source by most people's definitions, and certainly not open science. So there are some applications, even in the geosciences, calling themselves open science, but they're absolutely not. While some data may have been released, they contain proprietary components, and so they cannot be replicated, and a certain amount of control remains with the proprietors. So it's important that we're not sort of misled in that area about the openness. In terms of security and privacy, any online hosted data, we have to be careful with what we upload, because once we upload data, we do give certain rights. It may be used without our consent. It may be used for training. So read the terms and conditions, opt out where you can sometimes of these models for your data to be used for training. And where you're not sure at all, just seek advice about using it. These free tools, as we know over many years, there's no such thing as a free lunch. So they're often offering capabilities in exchange for data. In some cases, we're very happy with that, as long as we go in with our informed consent for that. Now, there are general purpose large language models like ChatGPT and many others have been trained from vast amounts of the internet. So they have a good grasp of geological terminology. And this is because there's so much geological content on the internet, from geological surveys, institutions, academia, non-profit initiatives. One research study that was marked by geology professors scored these general purpose models at about 75% on PhD level exam questions. It can be different in other areas. So things like medical records, if you were training a language model, there's not a lot of that information on the internet. So there you would have to create custom models, but a lot of geological terminology already there. You can enhance this even further with a technique called retrieval augmented generation. And this is where you chunk your geoscience documents into a vector database, which you then feed into the LLM to further enhance your results. On the right-hand side is Google Gemini Notebook, which is free. You don't need to worry about building a vector database of your own content. It does it automatically. It's a no-code solution. And that uses RAG. So you can upload your own geoscience documents and then ask questions of your documents, summarize, extract data. It's a way to, shall we say, teach the large language model about geoscience or authoritative geoscience information, which is fully referenceable. But I don't mean teach in a machine learning sense. But if we don't use RAG, and the answers come from inside these statistical models, they can't be referenced. So in other words, we have no idea where the provenance is of the assertion coming from the language model. So that's why RAG has really been adopted by most organizations. It's really an information retrieval technique with a large language model at the end, because we can trace provenance. We can see where these AI generated assertions come from, which, for quite frankly, for geoscientists, if we can't have that, we're unlikely to trust it. One amusing thing with the Google Notebook is you can create your own webcast and actually be talking to your documents. Is a bit of fun. Underneath is an example where I built my own RAG solution. Very easy. You can do this in 1 or 2 days, and you can use your own local model, whichever you want, in the bottom right-hand corner. And just really to sort of show you how accurate some general purpose models are, I downloaded a small model from Hugging Face, which is a model repository, with several thousand petroleum and mining question answer pairs. And without having to do any specialist tuning, it had 94.5% accuracy. So there could be quite impressive accuracy for general terminology for some of these models. Now, there have been cases. This example I'm referring to here is Bloomberg, where they fine-tuned a language model for finance. There's some reports that spent about $10 million, but within a few months it was outperformed for most of those tasks by GPT-4. So it's a very fast-moving space. We have to be very careful of technical debt. Where we have current language models which are fine-tuned for geoscience, there's some evidence that actually they perform worse than general purpose models for a variety of reasons, such as catastrophic forgetting, where some aspects of the model are then forgotten as you tune it. So although you may assume that a geology-specific language model will outperform one of these state-of-the-art general purpose language models, don't necessarily use that as a given. In many cases, they will perform as good, if not better, and it's something to be aware of. So how can we use language models? We can use them as a Socratic partner to help us literature reviews, refine our writing, detect errors in our reports and those of others, and also support ideation. One of the interesting things with human AI teaming is there's some evidence that we can get more diverse ideas if we bring AI in the right time, not too early, but can help increase the diversity of some of the ideas. Prompting, interesting element, prompting, so providing questions, guidance, context to LLM, is rapidly emerging as really a core skill for AI literacy. Two researchers, even with the same discipline, can arrive at very different answers depending on their proficiency. So you think of the skill required to make Google searches. Prompting is almost an order of magnitude in its complexity and possibilities. So you can have two geoscientists asking the same question to language models, getting quite different answers. So I think it really moves beyond just a sort of technical trick to really be understanding how to prompt and get the best out of these models as a key part of literacy. There are other aspects of on the right, by the way. This is GPT-5 at the top, Perplexity at the bottom, and you can see these tools allow you to do quite deep research, simulate reasoning. Again, they both use RAG to crawl the internet for information to try and answer your question and reference it. So they can produce some quite interesting results to use for that. There are other uses which not every geoscientist might be aware of, but one key thing I think is that the geoscientist should always be in the driving seat, liable for results using AI tools, and bear in mind just how persuasive these tools are. We sometimes anthropomorphize the outputs, but we must check, we must apply critical thinking around these tools. That the authoritative information backs up any AI-generated outputs. Here's an example. We're not talking about generative now. This is extraction. So what we have here is a general purpose model. In this case, Anthropic's Claude 3.5. And we've got a log here with handwritten cuttings descriptions. And you see the prompt just asking it to extract those descriptions by depth. And again, it does a pretty good job with just a very simple prompt in this case. Spend a bit more time, could improve it. Again, just general purpose language model. So using this extraction, we could bring more data points into our models to help reduce uncertainty. And then on the right is using text embeddings. So This is turning the text into mathematical representations, here building a model from scratch. So really a language model, not a large language model. I've used 5,000 reports from the US Geological Survey. And what we're looking at here are minerals. So each of these is the dense vector, the embedding of the mineral, plotted on a TS&E plot, where you have minerals plotting close together. They share similar context. The words around them are very similar. If I look at the sort of bottom left, you've got scheelite and molybdenite, not a particularly well-known association that could have implications for porphyry scar mineral deposits. So again, real possibilities for scientific and business discoveries using these techniques. I released a model, an application, LLM-based application, just in August, really just to encourage experimentation, show people what was possible. So all the code is available. You can use whichever large language model, local, hosted, whichever you wish with it. It automates literature reviews, downloads the PDFs for you, renames them with the proper titles, creates knowledge graphs so we could see connections between different concepts, and you can modify those to different geological concepts that you wish to see across quite large volumes of text. And also map-based visualization. So at the bottom, we've got a query here, show nickel, copper, and gold in Namibia. And this queries the Hudson Institute for Mineralogy, MINDAT database. So it pulls in not just native, for example, for copper, not just native copper, but also minerals that contain copper like chalcopyrite, bornite, azurite, etc. So again, something to use. You can run completely locally on your own machine for privacy. So what does it mean, AI literacy? Obviously, we still need that core geoscience knowledge. We need critical thinking, not just when to use AI, but also when not to use it. Ethics, won't go into it too much detail, but the report was published yesterday. AI ethics recommendations for the geoscience community, and that's available to read. And also, of course, the data and technical proficiency. So how to use tools, how to prompt, but also understanding the math and stats behind it. Just like a car, we don't need to know everything about how a car works to be a driver, but it helps to know something, the limitations. And certainly, if we don't, we can make inadvertent errors by our lack of understanding around data science. I haven't got time to go in here, but of course, there's lots of training available to help understand. You don't need to be a maths genius or an expert programmer to improve your AI literacy. So maybe in all these areas, people can sort of self-assess themselves as to where they think their strengths and weaknesses are. So in summary, I think we need to balance caution. We need to be skeptical, but also keep an open mind to experimenting with LLMs. Question how AI is shaping knowledge, when we should use it, when we shouldn't. And again, perhaps steering this sort of pragmatic course, not listening too much to the end members of which you get in any sort of topic. May be able to help us in our work to better meet and serve society as we practice as geoscientists. One final thing, I've been writing a blog for 10 years on AI and geoscience, non-commercial, lots of links in there for tools, courses, articles, which may help people just starting out. That's all I have. Thank you for listening. Happy to take any questions.
Thank you very much, Professor Paul, for this practical and excellent presentation. We have a few minutes to take questions. So please drop your questions in the chat. So let me read this one out. Generative neural models that utilizes large language models, do you think may offer promising solution for accurately predicting earthquake and conducting stability analysis related to seismic hazards and mass movement? This raises a question of whether there is a genuine hope for advancement in this field. What would you say about that?
Yeah, I mean, my specialization is unstructured data, so I should give that as a disclaimer. But I think there is there's some promising research in that particular area, um, particularly around sort of explainable AI, because obviously one of the challenges with deep neural networks is that sort of black box element to it. But I think there's be some good work on explainable AI or XAI to try and understand the sort of different features and traceability. And I think that's the key element is being able to understand the results that are coming out. Um, but I believe I've read some promising research in that area, although it's not my area of expertise.
Thank you very much for this answer. For those who are dropping the questions in the chat, thanks so much. Professor Paul, your expertise is greatly appreciated. So without further ado, let's move on to the next speaker, Professor Glenn Naylor. Please join me welcome Professor Glenn Naylor with a virtual round of applause. The stage is yours.
Thank you. And just like Paul, I'm going to switch off my video for the purpose of bandwidth during the presentation, but I'll switch it on back for question and answer session. So what I would like to share with you today is a concept which comes from fintech and is known as sandboxes. And the main reason for doing this is the mere fact that we have so many people who are producing a lot of very useful tools, and most of them either never end up reaching the market, or some of them do actually get archives in academic literature and so forth. So what I will share here is more of a journey on how you can actually put together a number of very good research that may lead to something being deployed into the industry. So I call Sandboxes the catalyst of innovation in the mining industry. What I would like to focus on first is to share the agenda for this, that I will only give 2 case studies. But the first thing that I will do for those who are not fully initiated is to share what is a sandbox and what components of it actually leads. Yes, Natalie?
Sorry to interrupt. I don't see your screen.
You don't see my screen. Let's check it again.
You know, technical difficulties during an AI webinar.
That happens. At least you know I'm a human being, not a machine. Is it clear now?
Yes, if you just stick it in presentation mode, then all good.
Is it on presentation mode now?
No.
Really?
There we go. Perfect. Thanks.
Okay, there's just a bit of a lag. So as I've mentioned, I'll mainly speak of sandboxes as catalysts for innovation in the mining industry. And what I will focus on is mainly 3 aspects. The first one is just to share for those who are not fully initiated what are sandboxes. And I'll give 2 case studies, one mainly looking at mineral prospectivity mapping, the other one expanding to that using remote sensing and environmental geology. So to start off, for those who have never worked with sandboxes are typically quite well-structured framework, and they offer a very low-risk environment for testing ideas. So you will notice that we are in an era now, 25 years into the century or a quarter of a century, that there is a concept of hyper-innovation where new things are coming out almost every day. Large language models, as Paul has mentioned, are also coming out on a daily basis. But what is mainly missing is the route that typically one needs to follow to deploy a technology. And in mining, this is highly needed because not every technology that is being proposed comes without the risk. So we have to deal with the uncertainty aspect, and we have to do this in a human-centric manner, meaning that we need to look at the feasibility of the technology and whether it's desirable for the type of environment that we're going to be using it. And the last one is mainly the visibility aspect of it. So with this in mind, I would actually like to categorize two main challenges for the 21st century geoscientific problems, and they require actually two different solutions. The first one is a transformative sandbox, which is mainly a structured environment for testing a step change idea, meaning something that is quite new, that is going to change how we do work, how data flow, and even considered feasible, for an example, for deployment in different environments. So as you can see, on the animation on the right-hand side, it simply means that we are changing from one form to the other. The second type of a sandbox, I call it optimization sandbox, is mainly a controlled testbed for tuning very known processes. So it means we combine different knowledge systems, and we build something that is going to optimize the information that we know, and it's represented with the graphic that you see on the bottom right. So the two case studies that I'm going to share, the first one is mainly a transformative sandbox, and the second one is mainly a hybrid that has some elements of transformative sandbox, but it's mainly an optimization sandbox. So in order to do this, I'll move to the very first case study, which deals with mineral prospectivity mapping. So if you are a geologist working in the field, much of your tools that are available to you are mainly dependent on your skills and your training. So it means if you're a geophysicist, you are mainly limited to particular methods, such as potential fields methods that may include magnetics, gravity, and radiometric methods, such as uranium, potassium, among other type of tools. But if you're a geochemist, it means you also work in your own sphere. And if you work in remote sensing, you work in one sphere. But because of the complexity of mineral systems, which now represent what used to be active systems and are now fossilized type of systems, it simply means we need a tool that can assist us to delineate areas that are quite favorable for further exploration, but also going to be able to save us time and costs. And they also have to be environmentally neutral, because some of the places that we go and explore for mineral deposits are quite biodiverse and very sensitive. So the image that you are looking at here on the right-hand side mainly represent a combination of data sets which is prepared by a multitude of experts. But the problem with this is that one person has to do the processing. It doesn't mean that the fact that it was collected by many people, everyone else has to get their hands in. And this is where mineral prospectivity mapping that is data-driven is actually needed, because one needs to be able to pre-process this data to create one form of a uniform index and to also integrate it into a knowledge system, and finally come up with some sort of a modeling. But the starting point for it is to mainly understand the mineral systems, meaning it starts with the discipline expertise. So in order to do this, we have proposed a concept, because mineral prospectivity mapping is not a new concept. Actually, it's a concept that in the 1970s and 80s made GIS more popular to geoscientists. And it's actually now more enhanced because of the available technology. So just imagine yourself looking at all those multiple layers that were collected over time, and you can call them evidence layers. And you stack them into some sort of a cube, and we can just call that a data cube of some kind. And think of what you have to do in order to get the results before you do many processing, as you going into a dermatologist for a while, monitoring your skin condition, and they will take you a picture of before and after and actually see how you look like. So this is what you will do in all those particular layers. Sometimes it's more than 50 or 70 layers. And what comes out from it is more of a denoised and reconstructed features that enable you to do more things. So if you're interested in reading more on the details of the methodology, there is a link here for the paper that you can actually review. But what I want to share with you is the advantage of doing mineral prospectivity mapping in this sense. You can actually build thousands of models, and it's like each and every having more than 1,000 experts building different mineral prospectivity map, and you must treat them as scientific experiments of some kind, because each and every one of the outcomes is not always equiprobable, meaning that you can get different outcomes, but those outcomes, if you start now looking at where the experts start agreeing, or different algorithms start agreeing, it means you are formulating a scientific consensus using different machine learning algorithms. And then the right-hand side, the advantage of this is that you don't only get those thousands of models, you actually also get an outcome in a form of uncertainty modulation. And this uncertainty can take form in many ways, depending on the size and the area that you are planning to prospect. One, you can look at standard things such as the variance and standard deviation and see where there is no consensus. Secondly, you can actually look at something called the information or Shannon entropy, which actually highlights places that are quite favorable for exploration and places that you need more data, meaning that if you want now to prioritize where to drill next or where to follow up with more field work, you can actually choose the targets based on the information that you have. So if you are looking for something that is more specific, that will give you exactly something similar that is related to the reality, you can choose something like UDI, which is the Uncertainty Decision Index, that helps you to narrow down all the uncertainty in the maps. But this is only possible simply because there are a number of things that are required. So a survey that we have done, or we typically do these surveys annually, wherever we speak to a number of people who are working in this space, we have noticed that the main barrier in mineral prospectivity mapping, it's not the geo-domain knowledge. It's mainly coming from statistical skills, coding skills, GIS and cartography skills. Geological mapping, most people do have them, but in order to do such type of maps, it needs just a combination of skills. So my advice, which is actually to continue from what Paul has mentioned, is to say that first you need to know much about your discipline, but the future, in order to do much of this to compensate for some of this lack of skill, it's prompt engineering. But you need to do this quite well because, for an example, you can't go and ask a question of saying, write me a code that learn all the geology without a specific purpose and so forth. So prompt engineering has to be something that becomes your go-to as a learning journey to do much of this. Once you have mastered that, it simply means that you can actually move to the second space. And the second space is a case study that combines much of the transformative and actually optimization sandboxes. And why do I call this a sandbox? Just imagine a system that allows you to do a number of things. The first one, it's mainly to use dust particles in places that are quite arid to understand climate systems. For an example, if you have more of iron-rich and darker minerals and so forth, they tend to absorb much of the energy. So it means they actually warm the atmosphere. But if you have more of very lighter minerals and so forth, they tend to reflect much of the energy, meaning that they can cool the atmosphere. So what NASA has done in the last number of years, about 3 or 4 years now, is to actually launch a new satellite. It's a hyperspectral satellite, which is called EMIT. And the main aim for EMIT is mainly to look into two aspects. One, quantify uncertainty when it comes to climate models, because you'll find that the dust that moves from Africa actually ends up landing in Florida, for an example, and that also affects the climate there. But us as geoscientists, we're looking also beyond climate models. We're also looking at mineral exploration. So EMIT allows us to use mineral dusts to understand much of the composition of the minerals for relative exploration. And how this works is the following. One is that you have these hundreds of wavelengths that are actually stacked together in a form of a data cube that you see on the left-hand side. And EMIT is sitting somewhere in here, actually emitting or measuring dust and composition of dust, which tells us which minerals are being eroded from what regions and not. The second one is that we have the Copernicus Space Agency, the EU Space Agency, which gives us Sentinel-2 images. And we also have Sentinel-1, which is in SAR, and that also gives us the changes in deformation of the land surface. But we can also monitor the composition of the emissions in the atmosphere. So it means if you combine the integration of all these different systems, we can be able to do climate monitoring. We can actually do emissions monitoring, acid mine drainage. But for the purpose of continuation of with that example that I have given, I will look into mineral exploration, and towards the end, I'll touch on emissions themselves. So this is an example of how EMIT produces data. So it actually, you map out a surface in arid areas. You actually look at the dust that is being eroded and the wind direction where it blows and deposits some of the spectral signatures of unique minerals. And for an example here, this is an iron ore deposit. There's an iron ore deposit very close in here, and you can see the typical dust signatures that are being emitted from that space. And if you zoom in further, you can actually see where the mine is located, that you do have hematite and goethite at some of the minerals that are being emitted and being monitored by EMIT. But if you take these and you add Sentinel-2 and you build a spectral indices cube with Sentinel-2, it simply means that you can actually reverse engineer the process of having satellites that have limited bandwidth combined with those with higher bandwidth to do something like this. And it's more like finding the needle in a haystack in exploration, because you take those individual indices or individual bands that are coming from a multispectral remote sensing, and you use the EMIT satellite bands to actually predict the composition or variation that you find in Sentinel or multispectral remote sensing, and that will highlight or enhance the signal of an iron ore deposit. And this is an example, and you can go and read the paper about it. We have written about it on how this deposit was actually discovered by some of the work that we have been doing using reverse engineering of satellite data. The other aspect that I want to look into is something that has been under research for a while, but it only became known to much of the public, I will say, in 2025 or from 2024 and 2025. And this is by Google DeepMind, which is a concept of satellite embeddings. And satellite embeddings, for an example, coming from this Alpha Earth Foundation, simply signifies the following, is that you take all those satellites that I have mentioned, all the data sets that they have, you use a similar process, similar to what I have showed you when I showed you an autoencoder that shows a face before and after, and you create embedded vectors that represent all the spectral signatures, not in a native form, but more in a latent space. And what you can get from this is that each and every one of those pixels that you see on an image embed about 64 vectors of different satellite data. The other one is that the opportunity of this is that instead of you looking at Sentinel alone or looking at EMIT alone, you actually fuse multi-sensors and unify the representation of data over a continuous space. This assists on something that we tend to struggle. Usually to do mineral prospectivity mapping, it means we need to clean up one of those layers and pull them up one by one and translate them into a latent space or do principal component analysis. But with this, now it simply means you no longer have to do that, at least for 2D mineral prospectivity mapping. The other thing that you can do is mainly similarity search for analogs. For an example, find places that looks like A, B, C, and D and give it an image that represents a particular deposit. And what you see here are some of the embeddings. And in reality, you can actually apply them like this. So this is what we typically do when we do standard mineral prospectivity mapping using autoencoders. But when you now use Alpha Earth Foundation and those 64 embeddings, it means you can even do time series analysis of the changes in the land surface, the location of where the mine is located, and you can actually track these using a number of those vectors that are shown in there. So the advantage of this is that you can actually do multi-purpose type of mapping. You can map for exploration of mineral deposits. You can look for land surface changes, but you can also do climate monitoring or modeling if you are interested in that type of science. And this is an example that shows exactly the same space of a mine that I have showed you using the fusion of EMIT and Sentinel-2. In the interest of time, I just want to close with just two things. The other thing that we have been doing in this particular space from all that knowledge was to create a variational Gaussian processes algorithm that can actually take individual drill holes that were drilled in those sites and create implicit geological models that are compatible with commercial software for visualization, but you can also visualize this in Python. One of the things which is the benefit of that is that you can also trace the amount of emissions that comes from regions that are known to be mining things such as coal, or where they are burning fossil fuel for CO2 quantifications and so forth, and trace the wind direction or the distances that emissions actually flow. So in short, the advantage of having sandboxes is that, one, you have faster learning loops, because all this knowledge, it means, is compiled by a number of people. You put it in a system that allows you to test it a number of times in a research format, but you actually move away to deployment or piloting, having gathered more evidence using artificial intelligence as a group of experts. The second one is that it now permits, much of these models that you see permits inclusive collaboration that surfaces diverse perspectives, meaning that roles that were typically reserved for a particular gender can now be passed across, and people can collaborate well in different levels and so forth. The third aspect, as a takeaway message, is that we still have an issue of hyper innovation where things are being proposed, not tested, and they go for deployment, which creates a lot of challenges in the mines and makes delays in terms of adaptation of technology. So sandboxes actually reduces that risk, because you do all this test work and stress tests before you deploy any particular technology. The last one is mainly dealing with hypothesis testing, to say that this allows you to build thousands or hundreds of models for your particular purpose, be it geological exploration or climate monitoring or environmental monitoring. And I believe that the easiest way to do this, there are companies that are already doing this, where they scout the different research that is being done by different universities and convert that into test pilot cases as sandboxes. And from there on, by the time that they deploy this to the mines and so forth, there's already research that is backing up what they are talking about, but there's also SOPs that provides guidance and limitations of it. And in short, I believe that sandboxes are the future, and universities could be the neural conveners of sandboxes, because at least they are not doing this on a commercial scale, but to actually assist the industry and working together in a piloting type of a phase. So in order to do this moving forward, it simply means that we need to move away from how we do things, and we now need to be an upright type of a human being using AI as an accelerator for the decisions that we make. Thank you.
Thank you very much, Professor Clay, for this insightful presentation. This is fantastic. So we will also be having a Q&A panel. So we don't have much time now, so let us just pick only one question. Then we invite all the speakers for the live Q&A panel. There's a question here. Let me just pick one. Okay. What strategy would you recommend to overcome the skill barrier?
I think the first thing is to actually choose a particular problem that you want to work on, because you can't just learn all the things at once. So how I started, for an example, around 2014, that's when I started actually doing or building machine learning type of models. It was, I had a problem that I couldn't solve using traditional type of solutions, and I actually used that as a starting point. So all the toolkits that I have built up over time emanates from the single problem that I was working on. And as you grow and mature and so forth in that particular discipline, it means you build more toolkit and you now know where to go. So large language models, for me, I think they are the best ways, because if you didn't do any degree in computer science, it simply means that it's like learning to speak a new language. There are specific things that you learn only as a kid, and large language models are actually an opportunity to learn things that no one will ever teach you when it comes to coding or statistics or basic ways of interacting with AI.
Thank you once again for this insightful answer, and thanks for those who are posting their questions on the chat. So now we have a live Q&A panel where all speakers will be available to answer all our questions. So I would like to hand over this this section to Natalie Brown. She will moderate that part. So please keep dropping your questions in the chat because this our live Q&A panel is going to be very fantastic. Hi, Natalie Brown.
Thanks very much, Andrew. I'm going to hand over to Lovemore to field these questions. There are a few that are still in the chat. Lovemore, I don't know if you want to start with those. Alternatively, if there are more questions, please post them in the chat. Are you happy to go ahead, Lovemore?
Thanks, Natalie. A few questions that have not been answered. I'll start with a question for David. This comes from Enoch, and apologies if I don't pronounce your name properly. He apologizes for a lengthy question, which says, when we refer to both quantitative interpretation and reproducibility in the context of digital outcrops, does this imply that the digital outcrop can be accurately analyzed from geomorphological, geological, and stratigraphic perspectives? For instance, if one aims to assess the economic value of geological resources, this approach should certainly lean towards quantitative interpretation rather than qualitative. Additionally, what is the confidence level regarding the accuracy of interpreting natural phenomena, exact physical preferences using digital outcrop technology?
Okay, that's a really good question, or a really good set of questions there. So let me just break those down. So the first one, digital outcrops, can they accurately analyze geomorphological, geological, and stratigraphic perspectives? Yes, absolutely, you can. If you can see it and measure it, you can get it from a digital outcrop. The thing is that when you're dealing with field data and you're out in the field, making accurate measurements is often more difficult than you might think, because, you know, if you want to measure the true thickness of a bed or true thickness of a unit, it's quite often an estimate because you can only measure direct distance, and then you're trying to work out what the dip is and how that affects that measurement. If you're doing that from a digital outcrop data set, you can take an orientation, attach it to a measurement, and get a very accurate, true stratigraphic thickness. Apply that to your sedimentary logs. As you're going through a sedimentary sequence, when doing a sedimentary log, you're always trying to measure true stratigraphic thickness. If you've got observed thickness and orientation, then you can calculate that and get a much better representation of it. So there's an estimate that you do in the field, then you get rid of that estimation when you do it on a digital outcrop. So I think, yes, you can definitely do very accurate analysis, and you can do it on larger scales than you can do standing in the field, because yeah, you can see your outcrop from different perspectives. You can make measurements much bigger on things that are much bigger than you can physically measure in the field. So all of those things together really do mean that you can get a huge amount of information from geomorphology through to the geology. Assessing geological resources, that's where outcrop models like this really come into their own. So there's two different ways you can use it. As a direct measurement, you can imagine mapping a mine, like an open cast mine, and being able to make direct measurements from that, and doing that repeatedly on, you know, a daily basis if needed, and being able to produce very detailed change measurements as you're developing your mine. As you do that, you can start to pull out fault geometries and start to map those not just on an outcrop face, but slices as the mine is evolving. We use digital outcrops for subsurface characterization. So for any challenge where you're working on something that you cannot see normally. So that can be geothermal, it can be nuclear waste storage, it can be traditional hydrocarbons. we're working on the geology that we can't see. So we need outcrop data to help us understand the things that we can't see. A lot of those techniques and a lot of those industries need statistics and need information to be able to help understand and build models of the subsurface. And we can pull out those detailed statistics from outcrops. It's incredibly difficult to get them using traditional field techniques, but with digital outcrop models, we can build pretty robust statistical databases. So I think that might have hopefully has answered all of those questions.
Thank you very much, David. I'll jump to Glenn. A question comes from Sean. He asks, how does the resolution of EMIT and Sentinel compare with that of Landsat 9? Would you recommend one dataset over another in terms of open access datasets, or does it depend on what you are looking for?
So EMIT actually has a coarser resolution of about 60 meters, whereas Sentinel-2 do have pixels that ranges from 10 meters to 20 meters, and about 2 of them or so that are about 60 meters. And Landsat 9, including 8, do actually have more competitive advantage when it comes to resolution compared to EMIT, because I've mentioned that EMIT gives you about 60 meters. But what we typically do to integrate them is to regrid or discretize the blocks of EMIT into similar sizes of 10 by 10 meters and do the same thing for Landsat, and we do the same thing for Sentinel. So I will say, in terms of choosing what to do, EMIT is quite nice when you're actually looking at things in a regional space, because you get more information, so there's no gaps in the wavelength, whereas Sentinel and Landsat are more of comparative or competitive in a sense, except that Sentinel gives you slightly more on a shortwave infrared and near infrared type of wavelength, which gives you more information or details. So we typically use EMIT for more of large scale processes. That 60 meter pixels or 60 by 60 are going to be sufficient. Whereas when we stack them together with Sentinel or with Landsat, it means we're also looking for localized features. So that's how I typically do. It's so easy to get the data nowadays because all of them are housed in one place. For an example, Sentinel and Landsat are all in Google Earth Engine. So I pull them using Python, from there. For those who prefer Java, there's even templates of Java scripting that comes from Google Earth Engine that you can use. And the EMIT dataset still comes directly from NASA, but the satellite embeddings that I spoke of last, you can actually also pull them from Google Earth Engine. There's even a platform that I have actually used to create some of those maps that you have seen, which is very easy to use or quite friendly. I can share the link here.
Okay, thank Dave. Another question from Marina. The mining industry is quite reluctant to innovation. How can we encourage the use of new technologies within our teams or companies? I like the idea of the sandbox. That's a question to Dave.
Oh, to me, okay.
Sorry. My mistake. This is to Glenn.
Yeah, I thought.
Sorry.
So I used to lead one of the research institute called the Wets Mining Institute, and our role was to mainly assist the mining industry to select which technology is going to be reliable and so forth. So most mines will actually be reluctant to adopt any technology that was never tested anywhere. So my suggestion is that for anyone who's willing to sell new technology or coming up with new things, it's far much better if you spend a bit of time on a sandbox type of an area, where nowadays we even have more of mock mines. So here in South Africa, we have about 2 of those mock mines. I know in Sweden, they also have about 2 of them. And those mock mines then tend to be used as the test beds or the sandboxes where technology is tested and many people can actually vouch for it before it goes into the market. The reason most companies are saying that we are hesitant to adopt new technology is that when things starts failing, when they are deployed underground, for an example, the person who carries the cost is the mine, it's not the supplier of the technology. So they are quite skeptical to adopt new tech on that basis. And this is why I came up with the concept of a sandbox idea, because the technology that we ran using a sandbox are the ones that most of the mines that we work with ended up adopting, as compared to where technology was developed and deployed directly without any backup research.
Thanks. I go to Dave this time. The technology you shared with us, has it been trialed in underground mining to map and visual structures? Sorry, I'll read that again. Has it been trialed in an underground mine to map visual structures and reef zones?
Yes, it has been trialed and used in mines. One of the early projects that I worked on was using laser scanning in some of the old mines around Alderley Edge. We used that for fracture analysis studies. That was quite an academic exercise, but it showed how the equipment can be used. If you're working in a mine, it tends to be LiDAR rather than photogrammetry because you need good lighting for photogrammetry. You can do it with a very big flash gun, but we find that laser scanning is a much better approach when you're working in mines. And a lot of mining companies use laser scanning as a fairly standard thing now. So it has been used, and I've seen several examples of it being used for working in active mines.
There's another one for you, Dave. Since drone platforms are moving towards hyperspectral LiDAR and thermal imaging integration, what are some of the challenges, computational or geostatistical, that are faced when fusing the drone data with geological field observations?
I think that a lot of the data integration, we've kind of got it sorted. We can do a lot of it. The problem that you have with the different sensors with the hyperspectral LiDAR, hyperspectral imaging, is expense. They're expensive systems. It's also quite difficult to calibrate them correctly. That's a big difficulty with them. A lot of the commercial systems that you're getting now are on drones that you can buy readily are multispectral rather than hyperspectral, and not always in the relevant wavelengths for geological analysis. They're much more aimed at agricultural practices. So I think that in terms of the challenges of using the data and integrating it, we can do that. It's still the cost of hyperspectral systems and the challenges in processing the data, because you're using natural light sources, obviously you use the sun, you get variabilities of the lighting during the time of the data acquisition, the general sort of problems with hyperspectral. So I think that's where we kind of with that. I mean, people are using thermal imaging on drones for monitoring volcanoes. So that's sort of used quite easily. And actually, if you've got a thermal image, set of thermal images, it's just the same process as building a normal model.
Thanks, Dave. Paul, a question for you. Have you experienced GeoGPT? What are some of the noticeable technical challenges when applying LLM in geoscience?
Yeah, there's a number of systems called GeoGPT. So I guess if you're referring to the one from Deep Time Digital Earth or Zhejiang Lab, I've written quite a bit about that. There's been some letters published in the Geoscientists magazine, so people are free to read that. I don't think I particularly want to say anything else about that. I think the challenges around deploying LLMs in geosciences. I mean, organizations have some challenges because a lot of their information is confidential. So they're looking at trying to create systems behind their firewall. So that means either forming different agreements or using local models. And I've certainly encountered a lot of organizations struggling to get all their content together because, just like sort of Google search or any sort of corporate search engine, I mean, you want to search everything. I mean, why would you ask a question of something that doesn't have all your content? And that all has to be vectorized. So there's a lot of plumbing. It's very boring sort of side of AI, but it's all about the data, the completeness, the quality of it. And as I mentioned with retrieval augmented generation, this is really a fundamental point, is that the answers are almost determined to some extent before it ever gets to the large language model in a retrieval augmented generation configuration. And so how all that is put together is very important. So it can all then be referenced when you have the answers. And I think we're still in quite early days having that organized. But that's really what the direction that I see is essential for science, because when these models first came out, they were just producing AI outputs with no references at all. It was like reading, like a literature review where no one has actually referenced anything about where they got any information, and you can't trust that. We need to have transparency, and for people to be able to check where information has come from. So I think those are some of the challenges that I've observed.
Thank you. Thank you, Paul. Glad you're popular today. Hanok again asks, AI literacy, as you have mentioned, does not require one to be a math expert. However, I noticed that cosine similarity was included in your presentation. How effective do you believe cosine similarity is in the context of geophysical interpretation?
That's a very interesting question. So cosine type of modeling is mainly very useful when you are mainly looking at shapes and patterns. Traditionally, we used to do something called spectral angle mapper for hyperspectral images and so forth. But when it comes to things that deals with changes in amplitudes, things that are quite noisy or low signal to noise ratio windows and spatial temporal structures, it actually doesn't work, because cosine then becomes a pointwise in feature space, and it doesn't respect any form of time lags. So it depends on the context that you have to apply, but I typically use it for satellite embeddings and where I do have clear patterns and so forth, but I tend to avoid it when I'm looking at spatial temporal changes.
Okay, all right. Another one for you. Is there a radiometric measuring system suitable for drone mounting?
I'm not a drone expert, so I will actually defer that to David. I hope he can actually assist with that. The drones that I have used are quite commercial and freely available, but maybe David can speak a bit on whether we can mount radiometrics type of spectroscopies on drones for the purpose of these.
Dave, would like to pick
Yeah.
that on up?
I have seen some examples of people talking about it in conferences, but I've not seen any concrete examples, I think is the best way to say it. So I think people are working on the idea. I mean, as soon as you get to larger payloads, which is what you'd be talking about there, the legalities of using drones sort of gets so much more, so much more difficult to actually use them. The kind of drones that I use, the small ones, they have very quite easy in terms of getting permissions to do it. So that's the real big problem. And then I think for a lot of these sort of larger equipments, it's still small aircraft and helicopters that are used to deploy them. So I think it will happen, and there's evidence of it actually starting to happen, but whether there's much out in the commercial world at the moment, I don't know.
While you're at it, Dave, when taking the difference between two digital outcrop models, how is the true difference differentiated from variations resulting from two different data capturing events or platforms, that i.e. offsets of one data set to another for points that have not changed over time? Or is this not an issue because the outcrops are small compared to other geological or mine features that are surveyed?
Really good question. I like that. What this person's pointing out here is that I mentioned that I'd used two different drones on that data collection exercise. So I didn't actually collect that data to do a difference analysis. I was actually doing it to compare the behavior of the two drones, and the difference analysis kind of fell out of it. What you saw on those images, I actually imposed a threshold. So differences of less than 5 centimeters were assumed to be negligible. I put that as in differences in the drone. So all of the data that you saw, those changes were fairly large scale, so greater than 5 centimeters. In terms of validating them, you can just look at the images and see that between images from different years that the blocks have fallen off there. So it does work. I think there is some difference between using different direct platforms. If I was doing that properly and it was a planned exercise, I would use the same drone each time, obviously. But I would go even further than that, is that I would use a preset flight plan and follow exactly the same flight plan, try and fly at the same time of day, and minimize the amount of variability between the different data collection exercises. But in terms of actual results on that outcrop, the outcrop is fairly stable. It's pretty hard, doesn't weather very much. The ironstones are really tough, and the variation that you see on those images is real variations, but I wouldn't trust that data for sub-centimeter variation or variation on a couple of centimeters. But for more than 5 centimeters, I think it does a pretty good job. But if you wanted more, you would have to put a lot more time and effort into planning your data collection.
Thanks, David. Thank you so much, Lovemore, for handling that. Sorry, I'm going to have to cut you off just because we can sit here all day and answer all these questions. I have collected all the questions that have been unanswered. What we will try to do is compile them for you, and maybe we'll put out a post or two answering the remaining questions for you. But I'm sure if you reach out to David, Paul, or Glenn on LinkedIn, they'll be happy to answer any more of your questions. Yes, look out for all of their recent publications. There's really some interesting work going on in this space. So on behalf of the AIPG, the GSSA, the WAIMM, and the GSZ, I'd like to thank our speakers for this insightful session. It's really an honor to host a panel of such stature. So thank you so much, David, Paul, and Glenn, for your contributions. As always, these sessions would not happen without our participants. So thank you for your great questions and enthusiasm. Lastly, I'd like to thank the organizers of this webinar, as well as our incredible support team that have been handling our Zoom and YouTube platform at the same time. So thank you guys for that. Be sure to look out for any more events on our social media pages and in the newsletters and things like that. Follow us, look out for the next one, and have a good evening, everyone. Thank you so much.